Recently, I shared a video discussing methods of dynamically lighting 3D models which were textured using traditional methods. However, labeling this video as a discussion of lighting methods was a bit misleading. All models were lit by the same method, with the differences actually being produced by variations in the normal maps. I made this distinction to ease you, the viewer, into the concept of normal mapping, but now that you understand what normal maps do, it's time to explain a bit further. First, I'll recap the key points from the last video. We know that the brightness at any point on an object is calculated based on the distance of that point from a light and the angle between the light vector and normal vector. We similarly understand that a colour map, like a diffuse or albedo map, is used to specify the base colour of that point, and that a normal map is used to specify the normal vector at that point. The part I didn't really elaborate on is what we do with the brightness value once it has been calculated. How do we actually put these values together to make an image? Modern rendering is entirely possible because of the GPU in your computer. But what does the GPU actually do which makes it so good at rendering compared to the CPU? Both the CPU and the GPU run computer code, which is essentially just a set of instructions that the computer follows, the same as how we might follow a recipe. Let's consider that all the instructions that the computer follows to render a single pixel on the screen is packaged into a block, which must be run independently from the instructions of any other pixels. This means that to render something to the whole screen, we need to run this code block a separate time for each pixel. For a 1080p monitor, this means our code block will need to run over 2 million times every frame to make a complete image. This code block always takes some amount of time to finish its set of instructions, but computers are pretty fast, so let's just imagine for example that it takes 1 millisecond to prepare 1 pixel. On a CPU, blocks must be run in sequence, meaning that we run one, then the next, and so on. If we use the CPU to run our pixel rendering block for every pixel in sequence, it would take around 35 minutes to render a full 1080p image. In other words, we would achieve a frame rate of 0.0005 frames per second. On a GPU, however, blocks are run simultaneously, meaning that we can run the code block for every pixel on the screen at the same time. Now it takes roughly the same amount of time to render the whole image as it takes to render a single pixel. We could render an entire screen 1,000 times in a second. The GPU has a lot more limitations in how complex the instructions can be, but it is essentially always faster at running simple independent tasks many times over. We call these GPU blocks shaders because they are typically used to render shaded 3D objects, but anything that's rendered by your GPU is produced by shaders, including 2D games. This begs the question, how do we make a shader to render our painted objects? As always, we need a new painted 3D model for this video. Since we're looking at shading methods, how about something bright and colourful, like this parrot? There, now we have something to work with. Let's try to make some shaders that light our parrot properly. I'll represent the shader as plain text, so it's easier to understand what's happening. You can read it the same as any set of instructions. The GPU just follows each line in order. The shader is given a few different values by either the CPU or by another shader which has already been run. These are called inputs, and for the painted shader we'll just consider the diffuse color, normal vector, and light vector values at whatever pixel the shader is being executed on. We'll give this shader a single output, which is the resulting color of the pixel. This is the color which will be displayed on the screen. The most basic shader is to just return the diffuse color. Suddenly our parrot has appeared. This was the shader which I used in my first video, since in that video the lighting was painted into the texture rather than being added by a shader. Now we can take the normal and light vectors and use these to calculate the brightness value as I described in the last video. Then we apply the lighting by multiplying the diffuse color by the brightness value before we return it. Clearly this does not look very good, and at this point I need to admit a lie. In my last video I showed you the object looking like this, but the simple lighting model I described will actually only look like this. Although we can vary the normal vector at each point by changing the normal map, we cannot change that the shadows are pure black and that the more shaded colours look grey using just the normal map. Obviously I used a better lighting model to show you the effects of normal maps in the last video, but now it's time to be more honest. This is how our parrot looks with this basic lighting model and the brushstroke normals. Let's try to make it look actually good. The main issue that we want to deal with is the lack of any light in the shadows. While it is possible to have completely black shadows in real life, it's not a regular occurrence. Outside of select circumstances, like floating in the vacuum of space, there will always be some amount of light bouncing around in the general area around an object, as well as from a direct light source. For those of us within Earth's atmosphere, the sky provides a relatively constant field of blue light from above during the daytime, meaning that shadows are just a bit darker and bluer, not completely black. Similarly, indoor objects will be hit by light reflecting around the room as well as just light directly from a light source. This is known as ambient brightness, the amount of light that will hit an object which is not directly from a light source. As before, we don't want to do any ray calculations to determine the ambient brightness of the object, and if we ignore reflections we don't really need to. Instead, we can just specify a fixed ambient colour, such as this light blue, multiply it by the diffuse colour and add this ambient colour to our lit colour. This is a fairly standard method of making shadows look better, but there is one issue for me. I don't have very much control over the colours in the shadows since they are just the original colours multiplied by the ambient colour. If I were to paint my parrot traditionally, the colours of my shadows would not be a simple tinting of the base colour, since this wouldn't look very interesting. Instead, the colours change as we move from light to dark. Is it possible to take more artistic control of the colours of our model? Let's consider a slight modification of our ambient lighting methods and take a more stylistic approach. We imagine that the shadowed areas of the model are represented by a single solid colour. Instead of tinting our diffuse colour by some ambient lighting, we can just directly add an ambient colour to the resulting pixel colour. This doesn't look good yet, because we are not only adding this colour to the black shadows, we are also adding it to the light areas. Although we have the right effect in the shadowed areas, the lit areas look pretty bad. We want to add less of this ambient colour in areas that are brightly lit, so that the ambient colour does not override the colours which I actually painted. The method of doing this becomes fairly obvious if we return only the brightness value we calculated. We see that the areas of the model which should look most like the painted colour are white, and the areas which should look most like the ambient tint are black. When we multiply the brightness value by the diffuse colour, we see that the diffuse map looks normal in the bright areas and disappears in the dark areas. What about if we then flip our brightness value so that the areas that were previously black are now white and vice versa? If we multiply this inverted map by our ambient colour, we now see that the ambient colour only appears in the shadowed areas of the model and disappears in the light areas. Now if we add this modified ambient colour to the lit diffuse value, we see that the shadowed areas are the ambient colour, but that it doesn't affect the bright areas at all. We call this method of mixing colours linear blending, because the amount of mixing is directly proportional to the value of the light brightness. For example, if the light is at half brightness, the result colour is a 50-50 mix of both colours. Linear blending does still result in some undesired tinting of colours, and doesn't quite look correct in all areas. Is there any way to make these areas look more solid, so that the colours are less blended and we have very clear light and dark areas? Well, yes. We can just specify a threshold for the shadow by making a new light value, which we'll call the blend factor. Let's say that if the brightness value is less than 0.4, then the blend factor is 0. And if the brightness value is above 0.4, then the blend factor is 1. If we perform linear blending using this new blend factor, then we can see that there is a sudden jump between the lit area and the shadowed area. The border does look a bit strange and harsh, so let's slightly modify the blend factor to be a bit smoother around the threshold. That looks pretty cool. These solid colour shadows are interesting, but it's quite a specific stylistic effect, which is not perfect for every use case. However, there's no reason that we can only use a single colour in our ambient areas. We could instead use a separate diffuse map, just the same as we specify the colours of the lit areas with the map I already painted. Painting a new map for the ambient lighting takes a lot more time, but it does give us very direct control over the colours of our shadows and helps us produce a wider range of interesting effects. I'm particularly fond of the effect created by the paint strokes not lining up between the diffuse maps, so it looks like the brighter areas are being painted over an ambient base layer as the light moves. This effect is possible because we use a normal map generated from the lit diffuse layer. If we instead use a normal map generated from the ambient diffuse layer, then it will appear as if the ambient colours are being painted over a base lit layer. There are drawbacks from this mixed map method, with the main one being that we have simplified the relatively complex variation in lighting into only two states, light or dark. This means that a lot of fine lighting detail above and below the threshold has been entirely discarded. Of course, it's possible to bring back some of this lighting by painting more diffuse maps with differing light levels and adding new steps into our blend value graph. This would certainly create a really interesting and dynamic effect, but it would be incredibly time consuming, and it's also not really feasible to have many different images being blended simultaneously for a single rendered object. It would just take up too much storage space and it would take too long to compute. This method isn't really viable, except perhaps for a pre-rendered animation without many different assets. We need some other way of managing finer lighting. What else can we do with our lighting value beyond blending between different colours? Ideally, we want to be able to drive some interesting colour variations that are manually specified, but without taking up as much time or space as entirely separate painted maps. Fortunately, this is possible, but to explain it, I'll first need to describe a different way that we can define colours, instead of using the standard red, green and blue values I described in the last video. We consider that any given colour can be separated into a true colour and the darkness of that colour, such that by multiplying the true colour and darkness we would have the original colour. This darkness is typically referred to as the value of the colour. Now we consider that the true colour can be further split into two values, one named hue, which describes the position of the colour on the colour wheel, and another named saturation, which describes the vividness of that colour. For example, a colour with a green hue and full saturation would look completely green, whereas a colour with the same hue but a lower saturation would look more grey and less green. To create any colour in the visible spectrum using hue, saturation and value, we would specify the position on the colour wheel with the hue, mix that colour with white based on the saturation, and then multiply the result by the value. You may be wondering, what is the advantage of using hue, saturation and value instead of the standard red, green and blue values which the screen actually uses? The main benefit is that this definition makes it easier to understand something called a colour transformation, which is just a method of changing one colour into another. By rotating the hue around the hue circle, or hue shifting, we can change whether a colour is green or blue without affecting how dark or light it is. Hue shifts are generally described by values between -1 and 1, which stand for full 180-degree rotations anti-clockwise or clockwise respectively. Similarly, by modifying the saturation or value, we can change how vibrant or how dark the colours in an image are without changing the base colours themselves. We can describe the saturation and value changes as falling between 0 and 2. A value of 0 means that the colour is fully dark or fully grey. 1 is the original colour, and 2 means that the saturation is increased or the colour is brighter than the base. Using a simple modification of the light value in our shader, we could easily drive a colour transformation. For example, if we decided that when the light level was 0, then our colour should be hue shifted 90 degrees clockwise, then we could create a hue shift value which blends from 0.5 to 0 as the light value blends from 0 to 1. Modifying the hue, saturation and value of our diffuse texture based on the light value can give us back a fair amount of control over the coloration of our shadows. The only problem with this method is that a single colour transformation won't describe the desired colour change for every colour in the model. For example, let's consult the 2D painting of our macaw. As the light level decreases, the yellow feathers on the front should become more red and a bit darker, so we construct our colour transformation to make colours redder and darker as the light decreases. This makes the yellow areas look better. If we now look at the blue feathers in the 2D painting, we see that they should stay fairly blue, but become quite a lot darker. Returning to the 3D model, this is not what is happening to the blue areas. They're shifting towards green and not becoming much darker. If we modify the colour transformation to look correct for the blue feathers, it becomes incorrect for the yellow ones. We need some way of performing a different colour transformation for each different region of colour in the original map. Fortunately, many image editing applications already have features which let us do this, so I don't have to do anything. Krita, for example, lets us modify the hue, saturation and value using a curve line, which means that we can easily edit the colour transformation differently for different areas. By manually editing the original diffuse, we can create a digital darkness map which can be blended smoothly with the lit map just as before, to create a similar effect to manually painting the darkness map, but with less effort. Interestingly, it is also possible to compare the hue, saturation and value between the original map and the modified map to create a different image which defines the maximum colour transformation at each point. Then, instead of blending between two images, we could directly drive the colour transformations of the diffuse in the shader itself, using the comparison map to set the ranges of each shift. This method is different from a linear blend. We would rotate around the colour wheel rather than cutting directly through it. However, performing colour transformations every frame is probably excessive work for a real-time application, so just blending between images is good enough. While I don't think that this method is as good as the effect created by actually painting multiple maps, it's a lot more time efficient, allows for a wider range of shades of light, and still lets me have direct control over the colours in the shadows of my models. So there we have it, a few different ways to make our lit painted objects look better by modifying our shader. Obviously, in this video I've ignored that we could also render the object in a more traditional photorealistic way, which would make our models look like real objects that have been painted over. Maybe I will discuss physically realistic rendering at some point in the future. However, I think that for now, non-physically real methods can often provide more interesting results. Ultimately, with an understanding of shaders, we can really make our 3D art look however we want it to. I realise that I haven't given you anything new to play with in this video, mainly because I didn't have to. While other things that I've made previously are specific enough that I needed to make my own tools, shader development is extremely accessible. Many 3D rendering programs like Blender or Unreal Engine include node-based shader editors which contain built-in functions that let you create really nice shaders without any programming at all. Alternatively, if you do want to try out shader programming, Blender and Unreal have options letting you do that, and there are also easier options like online sites that let you develop shaders and see them update in real time. For this video I created the shaders using Blender's node editor, since this is what I use to animate and I know it's what most of you will use as well. I've included a link to a Blender file containing all the shaders I made, which you can find in the description of this video, so if you want to use or modify them you can. As always, go check out my other social media or my website to see more of my traditional and 3D work. If you'd like to try out the app which I used to make the painted textures and the normal maps I used in this video, the link to the GitHub repo is in the description. Finally, be sure to subscribe so you can see what I do on this project or others in the future.